the thing that drives me on, what I call dreams of great schemes, or DOGS for short, which is, how do you solve strongly nonlinear problems? The easy case is Navier-Stokes, and the reason why it's easy because we have extremely good intuition about Navier-Stokes as humans. This is our world, and we see clouds, we see rivers, we see everything. We have not nearly as good intuition about general relativity and quantum general relativity, and Young-Mills and quantum Young-Mills. But if we don't understand how to deal with strongly nonlinear field theory, classical one, like fluids, it's very hard to know how we're going to do a similar thing in quantum settings. Newton formulates the law of mass time acceleration. It's force. In 18th century, Euler takes Newton's law, a little pocket of mass times acceleration, the derivative velocity, is force in continuous medium. He invents what's called in 19th century fluid mechanics, late 18th and 19th century. And it has one peculiar property, which they didn't worry about so much, that when you look at the acceleration, it has two components. There is instantaneous acceleration, but then there is also convective part. Nothing very fancy, just expanding something as partial derivatives. And what was amazing about fluid mechanics, it was beautiful, they all did it. So, Maxwell, Helmholtz, everybody who did field theory, electromagnetic, also did fluid mechanics. And it's an amazing property that all predictions of fluid mechanics of 19th century are all wrong. None of them agreed with the experiment. They were so bad that engineers had to invent a new world. So they started doing hydraulics. So the engineer said, this thing is actually hydraulics, that's how it works. Because fluid dynamics would always produce a totally counterintuitive aspect of it. And this was fixed by Navier, who realized that, fluids are viscous, meaning if you have a layer of fluid and slide it over next layer. He did not have a molecular picture in mind, but what we know now is that we're exchanging molecules, and that works as a friction, because if this guy is slow, this guy is fast, the slow molecules will slow it down and they'll cause a force, which turns out in a leading approximation can be described by this term, which has viscosity as 1 over Reynolds number, and it has Laplacian in it in leading order. And we had this equation since 1827. We had it forever. But experiment was done. And a German experimentalist showed that this theory is wrong. He did a pipe flow experiment, the profile of velocity was wrong, so people ignored it. Now, it turns out the experiment is wrong, because now we do the same experiments, we realize we have to make them 20 meters long and half a centimeter wide, but here like a short, fat pipe, and it was just the wrong experiment. So that killed Navier. And then he was a chief engineer of Paris, built a bridge across Seine. The bridge fell down. And it wasn't his fault, presumably, but the bridge fell down, so his reputation was up. So now, totally correct theory. Stokes is a brilliant English mathematician, beloved by lots of mathematical physicists. In 1845, I don't know where he took these equations of Navier or he reinvented them, doesn't matter. He did a calculation that you can do, that we teach in continuum physics. You drop a ball in a liquid, and it has terminal velocity because there is friction. It's a beautiful formula. You measure it, there's nothing to discuss. So that's why it's called Navier-Stokes. It was invented by Navier, Stokes. And now, not much could be done with this stuff. And today we understand why. These equations, so simple. You can derive this in 2 consecutive weeks in continuum mechanics course. Any place, totally logical. Newton plus friction, that's what you get. Very complicated. And the thing that makes them complicated is this innocent looking term that came out from taking partial derivatives called convective term. So this is not like quantum mechanics. You can write matrices and diagonalize them. This is something else. And today we understand that what we do today, there's no way to do it in 20th century, and late 19th century, just no way. What they did instead is they did beautiful experiment and they developed lots of intuition about viscous fluid. So Osborne Reynolds did an experiment in pipe which studied onset of turbulence. He invented scaling, he invented lots of concepts which used today. They were all empirical and they were not connected to Navier-Stokes equation to the best of my knowledge. And there's a great deal of empirical knowledge in engineering because everybody has to deal with fluids, move with fluids. And I'm guessing there's like 500,000 PhDs on this planet of people who can write Navier-Stokes equations and do something with them in all kinds of fields. It's totally ubiquitous human thing. And there's a great deal of empirical knowledge. So that's how it went for quite a while until we got to the third millennium. And now things are happening that technology makes possible. I'll explain a little bit of it. So you can do a PhD thesis where you look at experimental flow in a plexiglass tube. And instead of doing some kind of silly hot wire experiment at one spot and averaging, you can see that fluid is full of structures. This is some kind of isovorticity picture it does. Once you have seen this fluid and you graduate student doing this work, you can even say what the Reynolds number was at which this experiment was made. So you have totally different capability because this is moving in seconds and electronics is working, 3 to 4 orders of magnitude faster. So we can look at this data, we can do amazing things. So we have different problems than they had for 2 centuries preceding, and only we can do it today. We can also do very good calculations, which you can do yourself on your laptop now because the software developed partially here, partially in every place in the world. Works very well for some iconic geometry. So this is an example of turbulence. It's called plane coed. So we have to have 2 sheets of plexiglass, let's say, moving against each other. And if they move sufficiently fast, the shearing will cause turbulent flow. And now you can look at this in great deal, experimentally also, but numerically amazingly well. And again, I don't have to tell you in detail what this is, but basically you're seeing rolls of fluid being caused by this shearing. And when you look at this, for a while you start to recognize it. So if I show you another plane coed experiment, you'll recognize it. And what it does is it does some complicated stuff. Its turbulence says that it never comes back to the original plane, just like the clouds never become the original color. But every so often, it decides to order itself. Now you see some kind of rolls. So there is a glimpse of some structure. You think it's going to die and just go rolls. And then it, goes apart, falls apart, goes on, and goes on forever, like this. And so we have numerics that's now become everybody's numerics. You can do it if you have some ideas about it. What do we learn from all these things as humans? We have much better intuition about fluid turbulence than we have about Young-Mills theory or something. Because we see, when you look up, we see that what I'm looking at is not a cow. This is the French pronunciation of chaos. It's not a cow, but it's actually, a shape that I call a cloud, even though I've never seen it before and never seen it again. How is that possible? Because when I'm slightly myopic, I recognize some structures that keep recurring. So the rest of this talk about theory and experiments all about, can we make this into mathematics? And can we, organize turbulence by saying this has name, this has name, this has a name? We follow Eberhard Hoff, he said, we have this equation since 1827. They're good. We've done measurements, but now we have done measurements. They have 100 molecules, and they still seem to be following Navier-Stokes. It's very good stuff. So our task is to find consequences of these equations, rather than being very intuitive and make brilliant guesses about statistics of turbulence. So this line of thinking uses the equations, finds its consequences. There are no statistical assumptions or anything. So that's called deterministic chaos or ergodic theory or something. You start from the equation, you find the consequence. Now, these equations, how do you think of them the way we think about dynamics? In dynamics, we think about some initial state of the system, some law, and it moves it to the state space. And how are we going to do that? For Navier-Stokes, which is describing continuous. So intrinsically, it's an infinite dimensional system. It works very difficult. And now we have lots of experience with these equations. So if you're, too coarse in trying to extract information from them, you end up on something called Lorentz model. You end up on something where you have, 2 or 13 or 5 or some very small number of degrees of freedom. You develop subject called chaos, and it has no relation to fluids by the time you have done this. Doesn't have anything. So Lorentz attractor is an example of it going on now. To actually describe turbulence accurately, we know that today, when we have smallest example of turbulent systems, we need at least roughly 100,000 computational elements, which you call the dimension of computation with dynamical system. Now, the way you do this is, there's thing called pseudospectral method. So you think of the velocity field that's, some 3 or 4 dimensional function that use pressures. And you say, well, there's some good basis to it in terms of set of functions that may be orthonormal, like, sines, cosines, or Chebyshevs, or whatever seems optimal. This is a question for good applied math. And then you convert your dynamics into dynamics on coefficients in the spaces. And that we call state space. And if you do this, looks nice, you can formally do it. But, we made some estimates. So for example, we estimated for our Navier-Stokes, the one that I showed you simulation of, we would need 10 to the 13 algebraic elements to stick into the machine memory and then integrate this as ordinary dynamical system. So that's not, doable. So what we actually do, we are forced to look at high-dimensional systems. And what fluid dynamicists have developed, a very difficult and long program over decades, they developed computational fluid dynamics, which is not a dynamical systems approach, of converting PDs and ODEs in the way we usually do it. It's a voodoo of very clever applied math, and it works amazingly well, amazingly accurately. And we will use this in the rest of this talk to explain experimental phenomena. It's very good. Now, the point of this talk is, to bring you in line with Eberhard Hoff's thinking. So we humans are plumbers. We think of fluids as 3-dimensional things in some boxes, surfaces, and we look at videos of these 3-dimensional things in time. So, so that's a human way of understanding it. But actual thing, and that's what was point of Hoff's paper, actual thing happens in a phase space, which is infinite dimensional phase space. In that infinite dimensional space, anytime I take a snapshot of fluids, And now this means I don't just take thing from the top. I have to take velocity field of the fluid every place within the volume I'm studying. So it's a high dimensional snapshot, but every time I take this, this is actually a point in some vector space, which uniquely corresponds to this photograph of turbulence. And the time evolution, Navier-Stokes, traces out a trajectory. Now, why am I emphasizing this? As humans, we cannot even visualize 4 dimensions. We have to be pretty smart to navigate 4 dimensions. And now we're asking you to think about 100,000 dimensions. You cannot do honest work unless it's tens or 100,000 dimensions. So you think this is hopeless because I have no intuition. But point in 2, 3, 4, 5, 7, 12 dimensions is a point. And a curve that goes through it, which is trajectory dictated by Navier-Stokes, is a 1-dimensional curve. And now the issue is, it has lots of dimensions, but if I'm smart, can I project it into 2 or 3-dimensional frame where it captures the important intuition about turbulence? And that's what you have to learn about phase space. It's very good to look at problems in 3 dimensions. There's lots of intuition having to do with dissipation and how you put the energy in, and there's a great deal of good intuition about it. But if you want to understand when 2 clouds look similar but not quite similar, how they measure the distance of that. And that you have to do in state space, that you have to do in this infinite dimensional space. And while fluids might look very floppy and uncontrolled to you, when you're in phase space, they're very rigid. The things they do are deterministic and they're organized topologically in very rigid ways. And they're not floppy at all, as you will see. So think in state space. It's possible. Now, in the math department, I have to show one of these. We have a state of fluid. We stick it in computational fluid dynamics algorithm, and that produces, by some magic, the state of fluid sometime later. And we visualize a dynamical system. So we go back and see, we reconstruct our points in our dynamical state space, and we get a portrait of it. And we have some norms, and we can compute these coefficients, the usual stuff. And you get to what I've shown you before. What you find out in these simulations in a 3-dimensional state space, that you have some kind of recurrences. You see the same patterns like this one. You see it over and over, but you're never really there. So there's some kind of shadows in the space, and we will explain how the shadows works. Now, if you go state space and choose an intelligent set of coordinates, which I won't explain in detail, but we have a tutorial online to teach you how. The same trajectory I showed you in this 3-dimensional picture in state space, it's some starting point, and then it does something in state space. But if you let do something for a while, you realize it's building what we call natural measure. It's building areas of larger and smaller density of recurring, which means in terms of cloud, how likely I am to see certain shape of a cloud. These are the 2 ways of thinking, and they have different powers, each one of them. So this one has an amazing thing happening, which we couldn't believe when we saw it first. If you actually find numerically exact solutions of the fluid, which I'll show you maybe 1 or 2, if you find an equilibrium of a partial differential equation, Navier-Stokes, in state space, there's just a point. Now, the turbulence means the point is unstable. If you perturb it, things fall apart. But it's unstable in a way that we know from the Lorentz chart. It's a very simple dynamical system. So we found out that we can map out the region that you saw the turbulence being confined to by unstable manifolds of some finite number of periodic equilibria, relative equilibria, or so-called traveling waves, periodic orbits, relative periodic orbits, etc. And this is beautiful. This is so simple. This is fluid. This picture is 10,000 pictures because each line is a video of behavioral fluid. So this has huge amount of information. It tells you that this particular shearing of the fluid that look like garbage and crap actually is organized in a very beautiful, rigid way if you're in state space and if you use intuition from the dynamical system. So now, if we superimpose this information we have about exact numerical solutions of PDEs, which is something that we only have been able to compute in the last 20, 30 years, it's definitely not time of Euler or time of Reynolds. Inside of this cage formed by stable, unstable manifolds, etc., is turbulence, these little dots in here. I hope you can see. And now our task is to organize that. And the way this organization works is it turns out that, we know this already from more dynamical system. We have a chaotic system. It kind of has a skeleton hidden from the eye because you never see it in an experiment of unstable invariant objects, equilibria, traveling periodic orbits. So here I'll just show you one of them. On the right-hand side is how Plummer thinks. On the left-hand side is how you think in state space. There's a periodic orbit. If you look at this looks like typical turbulent trajectory. If I didn't tell you it was periodic, you would never guess. And if you look, so it turns out, by the time I've shown you 20 pictures of this unstable relative periodic orbits in the turbulence, don't look like this. Human cannot recognize them at all. But if you're in a state space, they're very rigid, they organize everything, they're really beautiful things to do. So that brings us kind of to the next important thing. The next important thing is how it started. I said, you look at the clouds, you recognize them because you see glimpses of them. In dynamical systems, it's called shadowing. So your ergodic or turbulent trajectory every so often visits some neighborhood that you recognize, that you've seen before. So what's done here is on the right-hand side is one of these unstable periodic solutions of fluid that looks turbulent, but it turns out to be like a commercial that it prints it out forever. On the left-hand side is a turbulent state, just typical state. And it'll be in dotted lines until it gets close to this periodic orbit, which is a loop in the state space. And then you will look at them in a real space and you'll see that you can't tell them apart. So here is this, they look different. And suddenly I'm close and I can't tell any difference between the two. That's a shadow. Now this guy is unstable. So you're gotten close to it, but it pushes you away because it's unstable. And at this point you lose it. Turbulence goes its own way. And this is where we were maybe 12 years ago. A bunch of theorists and applied mathematicians have produced all these beautiful pictures. And you say, you're in some stupid little box, which is doubly periodic. Is that experiment that I was saying? Who knows what you're describing has anything to do with anything, right? So that's the rest what I want to tell you. There's a theory. And as far as we are concerned, theory and practice, it's the big deal. But then we have experimentalists, and that's really big deal. Because in practice, there's a huge difference. So now we are lucky at Georgia Tech to have a group which combines theory, numerical methods, and fluid dynamics on 2 floors of Howey. It's led by Mike Schatz and Roman Grigoriev. And a list, I hope I haven't omitted any of the graduate students have done it. Lots of aspects of what I just described was now worked out for real physical system experiments and numerical simulation for it. And this is, PhD per person. This is lots of work. It's very impressive. So, and this we could never do in, Euler or Navier times. This is really what we can do today. It's tabletop, so you can go and see these experiments. They're all like 20 centimeters or something. And it's 6 to 10 person years per experiment to do this thing. So here's the first one. The first one, they said, it's hard to do three-dimensional turbulence. So let's set up a physical setting where it's effectively two-dimensional. So, one example is planet Earth, for large scales, the atmosphere is flat. Now in the lab, there's a box. This box is, 18 centimeters by 22 centimeters. You can look at it. It has 2 layers of different fluids and has air on top. And the top fluid is conducting, it's electrolytic. There is an array of magnets. And when you send the current through this electrolytic layer, it experiences usual bending in magnetic fields. And that, instead of shearing surfaces, this thing is standing there, you have to go into some weird stuff of sending fluid for kilometers or something. It's right there. It's being sheared in bulk by these electrolytes. If you apply current J strong enough, the thing goes turbulent. So I'll show you how it looks. We will always represent it in 2 ways. So this left way, as you will see, you cannot tell where this was from the experiment or from numerical work, because experiment is so accurate in measuring the velocity fields every place in this two-dimensional fluid. Either think of it as two-dimensional configuration thing that's changing in time, or we think of it as a very high-dimensional vector in the state space. And these are the 2 ways I want you to think about this. They find this kind of solutions that I showed you in our model, but this is actually a 3rd floor Howey. So they find a bunch of periodic orbits. They're all unstable. For some reason, they feel let's just stick a letter U in front, but almost all orbits it's always unstable. That's the definition. And there is a long turbulent trajectory. And this is the gray area. You strobe it until you build up balance. Then you can see that they have orbits which are capturing parts of the behavior. And you can do stuff with that things. But here now comes the amazing thing. So I don't remember if this is experiment or theory, this measure. You're measuring the motion of the fluid and you're computing vorticity and producing color-coded heat map, etc. So that's what turbulence looks like in this particular system. It has some structure because the array of magnets that produce the structure, but it has a property that never comes back to itself. If you measure the distance between this image and subsequent image, comes close but never back. So that's how turbulence looks in this 2-dimensional experiment. And now comes the amazing thing. They have all kinds of numerical work that is supposed to describe this fluid, its correct boundary conditions, and all kinds of things having to do that you have 2 liquids and all kinds of real stuff going on into modeling, not just some simple bunch of Fourier coefficients. They have an unstable equilibrium. So they have a numerical solution which has a property, it looks like one of these wiggly guys, but it doesn't change in time. It's kind of distorted, but it stays there. And that one happens to have one unstable direction. And what they do is they start along the eigenvectors of the unstable direction. Now they look at experimental trajectory in an experiment until they find a state that's close to the equilibrium that you only have mathematically, because unstable equilibria cannot be reached, because they're unstable and you can get a but you can shadow them. You have seen this in simulation before when you saw these rolls. They were unstable and everything. So now what happens is you look at your turbulence, you find a closed passage. You see the pattern like that if you look at a two-dimensional picture. And now you run your system in real laboratory time units. And it turns out that the fluid, turbulent fluid, is following your unstable manifold. So the thing that was some kind of mathematical nonsense we produced 10 years earlier, now the fluid is actually following it. So the blue guy is the fluid. And you can, map your fluid in the best way to a computer code and run your computer code, try to do the fluid itself. And here is what happens. So there's experiment. This thing I showed you. There is unstable manifold. You compute it once in your lifetime. You have it in your pocket once you've done it. And then there is a numerical simulation. And you see, they follow each other. And they go for quite a while until the things fall apart because, unstable turbulent trajectory runs away. So it says that state space is full of these neighborhoods. Each one of them has a thing we have computed and put it in our pocket because you just have to compute this invariant solutions only once. And what trajectory is doing exactly what we started out at the beginning. It's following deterministic motions. It's not some floppy stuff. It follows them until it exits that neighborhood. Then you have to figure out where you are. And, it keeps bouncing around this neighborhood. And now it's an experimental fact. It's no more something that's in your eye. What it means is that you can use deterministic theory, no statistical assumptions, no prediction, to predict the weather in this particular two-dimensional system. It's not planet Earth, but it says that the state space of the system, so all possible patterns, is filled with neighborhoods. And you can use your pre-computed information about these neighborhoods to piece together a turbulent trajectory and say, it's doing now this, that. So I think it's amazing. It happened 5 years ago. So you should know about it. So that's the big deal. It's really non-trivial. It's number of PhD theses that went into this, It really required sweat, blood, and tears, and it's amazing what I did. Now you say, well, this is like this weird little box. Why do I care about it? No, I want to bring oil from Alaska. So I want to, tell me how to do this in pipes and not some contrived two-dimensional system. It's not climate and it's nothing. It just happens to be fluid. In the three-dimensional world, there's some geometries that are easiest to describe and compute numerically. One of them is a pipe, which is a very long pipe. And people do beautiful experiments in pipes. And within the last decade, they've explained the turbulence transition that Reynolds couldn't explain in the picture I showed you. So that's one of the amazing advances of our century. But the idea is a combination of statistical and dynamical ideas in that particular result, so I don't want to talk about it. The problem is this experiment, to do them well, and you're not the 19th century German who says French are wrong because you have a short stubby pipe. It has to be very long. It has to be on optical cables. It has to be very thin, perfectly machined. And it takes really good experimentalists to do this. And you have to run with the fluid to see the turbulence is moving. The other thing that we see COVID era, there are ducts. The air has to move around. You don't want to make a pipe, you make just square ducts to move the air. You see them in all the action movies where people running ducts, crawling ducts. So now what you can do with a duct, you can bend it and make a circle out of it. And that's what I call Taylor-Couette So Taylor and Quet proposed an experiment where you have two cylinders, which are long cylinders, and they rotate against each other. So it was not like plain Quet, but bent and confined. And the usual theory has to do with one dimension being very long and this dimension being compact. What they've done in Howey, they've built a duct so the height and the width are the same, basically. It's a square duct. On one side, you move a cylinder. So inside, there's a cylinder. Outside, you move a cylinder, and you start at the shear of this floor. Why would you do that? Because now you can have complete information about this flow, complete, everything. It's an amazing experiment. It took years to build, and it has years ahead of it that will be used, done by Chris Crowley. So there is a table, we have a bunch of cameras, very fast cameras. Then, 2 meters above, there's a 20 centimeter plexiglass thing that had to be machined and done, rotate, and you have to get the optical, indices, diffraction, everything right. So you can see it. Then from cameras, you can get the velocity, the entire wing of entire fluid every place. Totally amazing experiment. Very hard to build up and construct. And for us, what it is, we forget all the details. There are two disc cylinders with different radii, 1 and 2. They move at 2 angular velocities, and if I move them sufficiently fast, I'll get turbulence in between. So that's the real three-dimensional experiment. When it starts getting turbulent, you can start seeing pictures of turbulence over the entire volume, just like the original picture I showed you of pipe. But that was uncontrollable because that's a glimpse of something that just floats down out of view. Here you control the whole thing. So experiment is on the left and numerics is on the right. And then you can visualize it this various ways. Because you have continuous symmetry and you have symmetry in time, all solutions are called relative periodic solutions, meaning when you find some solution that has a shape that doesn't change in time, that's called relative equilibrium. And if you rotate your view with the velocity that goes around, it looks fixed. Point. So, Poincaré did this first to study Lagrange points and stuff like that in dynamics. So there are frames in which they're. So, and that means that you have an original frame, you have positive periodic motion because they're periodic this way, if you have a periodic solution. So you can visualize them various ways, and then you can build the same thing. You can compute number of them, and then you can compare them. The gray area in this projection is the natural measure of the attractor to check that things are embedded the way they should be embedded. And, now again, another PhD thesis coming in. They're hard to find these periodic solutions, but these people are good enough to be able to find them. And in a good projections from 100,000 dimension numerics, you can see what your solutions are and which ones are embedded in the natural measure as we just discussed. What now we can see for the first time, and I'll show you a video, we have now repertoire of these solutions, and the idea is that turbulent weather inside of these things every so often comes close to the shape, and then it tracks it for a while. So this is one of the exact numerical solutions which are happen to be Tora in state space. And the turbulent trajectory gets close to it, and then it stays with it for a while. And then it goes and visits another guy. Okay. So there is a turbulence in the system. Turbulence means not that you have lots of small structures that you used to, but that you have a deterministically chaotic trajectory. It doesn't come to itself, it's unstable. And it visits the relative periodic orbit. So now we have another big deal situation. The big deal. First, I showed you that in one fluid experiment, which is two-dimensional, the turbulence followed your deterministic theory that came from Navier-Stokes. It's correct boundary condition. Now they've shown, people in Howard, that turbulence in realistic systems like turbulent flowing ducts and pipes in 3 dimensions follows shadows, visits the Navier-Stokes predictions. So now we have moved from, saying statistics, this looks Gaussian, that looks Gaussian, and it, has some width scales like 3/5, etc. Now we come to what Hopf wanted us to do in 48. He wanted us to use the equations, derive the consequences. And that means that sometime, few PhDs ahead of us, you'll be able to predict the weather in this particular duct. Maybe at some point, Annalisa will be able to use these ideas for the spherical ball of water with streams above it, etc. And this is all equation based. This is not based by clever intuition about statistics, and it's happening right here. You might, I told you, we have an intuition, let's turn it into mathematics. That's what it is. We have done it. It's a big deal. This work is not my work. This is work of my amazing colleagues and students, graduate students, because there's a continuum from engineering, physics, mathematics. I mean, there's no known boundary and geophysics, etc. We are all in this together. But to conclude, starting this Euler, now we have a way that I couldn't possibly have, combination of ordinary differential equation of state space and computational fluid dynamics, which is how you actually solve PDEs. We have portraits of turbulence, which are, totally beautiful, recognizable portraits. We have numerical results. You can explain the rate at which things fall apart. The theory predicts stability and stability. We have, I haven't done it, but a heteroclinic connection. We can go from one neighborhood to the other and describe it. And we understand turbulent dynamics the way you want. And this will show up on my homepage, but all of these, when you click on them, you can download the software and you can do it yourself. The future looks bright. What do we actually do is, what he said, that's nice, get this picture. We finally have this picture, Hopf's state space picture. They said, more important than the picture is the probability distributions, it's gray zones I showed. People do it, it's called natural measure and ergodic theory. I've explained this geometry. So there's the rigid thing, that fluid that looks floppy is actually in state spaces on a skeleton of very rigid things having to do with invariant solutions of their manifolds, unstable manifolds. Now we have to put probability measure on it. And that's what most real research is. The greatest challenge for theorists came from there. And that's it. There's a book. It's a very expensive book, but for you, I guess.